our next speaker is Afshin NIKTASH from Maxim Integrated, and his topic for the next 15 minutes will be system-level energy considerations for battery-powered AI. You have the floor now.
Hi, everybody. Thank you very much for joining this presentation. My name is Afshin NIKTASH. In this presentation, I'm going to discuss the system-level energy considerations to create a power-optimized AI application. So I'm going to use MAX78000, which is an ultra-low power AI microcontroller, as the platform for this discussion. After a short review of the system, I'm going to go over methods, parameters, and knobs that are available to get the best energy usage. And we'll continue with the results of two applications, face identification and keyword spotting. So generally, AI algorithms are slow, pretty much power hungry, and there are a lot of computations involved. So for edge applications, we can offload the training to different hardware and make the processing offline. So we may not need to be worried about the power itself if the self-training is not in the picture. However, we cannot get away from inferences. Mathematically, the inference computation is a series of matrix multiplications, which is implemented with a triple nested loop on classic hardware. So the complexity is obvious in order of n cube. This is a very energy intensive task on a micro, and this is where the edge accelerator can help by reducing the energy and latency by order of magnitudes. And that was our goal, basically, when we started designing MAX78000. So MAX78000 is an ultra-low power micro with addition of a convolutional neural network or CNN accelerator. So you can see on the left side, it's a low power micro. It has a Cortex M4 ARM core. It has a RISC-V core. The RISC-V core can be used as smart DMA or can run parallel tasks with ARM. 512K flash to store code and weights, SRAM. It has power management, security, different clocks, different external interfaces, including parallel camera and I2S for digital microphone. So this is about half the size of the die. What you see on the right side is the CNN accelerator, and that's the other half. It has 64 parallel processor with dedicated memory and state machine to control the data process in parallel while minimizing the data movement. So with this engine, you can do up to 64 layers, 1024 channels, and up to 3.5 million weights, depending on the weight quantization. You can do 180 data dimension if the image is preloaded, or 1K by 1K if you're doing streaming. Now, one key feature here is that the CNN accelerator runs independently from the micro. So the micro can go to sleep or can do other tasks, and we will get an interrupt when the inference is complete. The accelerator can do 1D or 2D convolution, pooling, linear layer activation, and element-wise operation. So our goal here is to save the energy as much as possible for the battery-powered AI applications. There are different levels to tackle the problem, and starts from the chip design and hardware architecture strategies. But my focus here is more on the algorithm and application side. But of course, I'm going to use whatever is available from the hardware configuration to save power. From the algorithm point of view, the algorithm improvements have a significant impact. Examples are like when we can just do some of the DSP parts of the algorithm and convert them to an AI model, like frequency transformation, for instance. And we use this approach actually in the keyword spotting example we're going to see later. Any model improvement to find a smaller model with fewer layers, choice, if we can use NAS, for instance, for this purpose. And by reducing the number of layers and parameters, it will help with the latency and energy. Also optimizing the weights through weight quantization or quantization-aware training. These are also important factors to improve the power. Actually, we have an implementation of NAS that has been finalized and will be added to our toolset pretty soon. From the application point of view, code optimization, especially in the pre or post processing of the data, is important. Task scheduling to make sure that there is no data bottleneck, those are important. And depending on the use case, we can choose the best duty cycle, how often we should wake up and do the inference. And that comes in tandem with the available power modes of the micro, like low power, sleep, micro power, standby. Each of these modes have their own power profile with limitations in terms of availability of resources or memory access and accelerator executions. So the other factor is basically clock frequency, but I'm going to show a few of these items in the next couple of slides. Here, the chart shows the power consumption in different operation mode. You can see the significant power drop going from the active to sleep, and then from low power mode to the micro power and standby. When running in the sleep or low power, the CNN accelerator can be active. So the micro basically provides the data, goes to low power mode, and then gets an interrupt when the inference is done. In the micro power and standby mode, it's mostly used for the inactivity duty cycle. So one trade-off here is that whether or not the weights should be retained in memory, or we need to reload them every time. So for a given application, depending on the energy consumption in either cases, it may make sense to reload the weights. And that's what we're going to see in the face identification example. One observation here is that while we think that reducing the clock speed could help us, but it does not necessarily help. Because of the longer execution cycle and static power, you may end up with a higher absolute energy. Having said that, it may still make sense to go lower clock speed if there is a limited budget of instantaneous battery power. Another observation is to use the RISC-V, which is a lower power micro than ARM, to execute part of the applications, like some pre and post processing. Again, the caveat here is that the RISC-V is in the same clock domain as CNN, and it's half the speed of the ARM. So what we noticed in the total energy, again, the total energy may increase as the processing time expands. By using the CNN accelerator, we can see that the inference energy is no longer a major factor compared to the energy consumed on the application. Here we have a comparison of executing our keyword spotting inference on a Cortex-M4 versus CNN. So for Cortex-M4, we use MAX78000 which is one of our micros, which has bigger memory and can fit the model. And we use the exact same model with 8-bit integer with CMSys CNN library. And this is the first bar you can see on the left side, blue, 8.3 millijoule. Now the second bar on the same model, we use the same model, but on the CNN accelerator. And it's 0.14 millijoule. Compare this energy now with the application energy, the yellow one on the right side. And you can see that really the inference is not anything comparable, while the blue one on the ARM or on regular classic hardware, the application and inference are probably very comparable. This next slide, I'm gonna show you the system energy of running a face identification example. You can see our reference cube camera hardware on the picture right corner. It's using the Face ID to detect celebrities. In this model, the CNN generates a 512 embedding vector of the image, and then the post-processing is basically to calculate the distance with embeddings of known objects. The chart on the left shows the energy in microjoule for different tasks, from capturing and pre-processing the image, loading kernels, inference, distance calculation, and TFT display update. To improve the accuracy in this example, we actually do 3 inferences per image. And we move the face box slightly for each inference. So you can see that there's like a 3x in some of these legends of the measurements here in the graph, and that's coming from there. And for the duty cycle used in this example, it makes sense to reload the weights every time a new frame is being processed. The chart on the right side shows the overall duty cycle, and the duty cycle of each task basically for the overall processing is 323 milliseconds for a frame. And having said that, the inference time is just a fraction of that. Again, it's 14 milliseconds per iterations. And after this processing, capturing and processing, the micro goes to standby for like half a second, and then we redo it. The next example is the keyword spotting. The network is trained to detect 20 keywords. And in this example, rather than using DSP, basically, the classic way to get the ML spectrogram of the waveform and then to train a model with the audio features from the spectrogram. This is pretty common. We combine the spectrogram extraction and the feature detection, both in a 10-layer network, and trained it with the raw data. So this is one of the algorithm optimization methods I mentioned earlier. Here the weights are loaded only once, and the CNN accelerator will only run inference if the signal level of the audio samples is above a threshold. So the chart on the left shows the energy of the CNN blocks. Loading weight is 220 microjoule, going to data is 20, and inference is 148 microjoule. The chart on the right side shows the average power when there is a silence, or there is no inference in that case, or when there is a keyword. In that case, the inference and all the pre-processing, post-processing are going to be executed. So the difference is like 0.5 milliwatts. And it's worth mentioning that the digital mic here is sampled at regardless of silence, like every 250 microseconds. So generally for a power saving and better application, if there is like some analog filter or wake on sound microphone, just to wake up the micro only when there is an audio signal, of course, the micro could go in longer sleep and consume less power. So this concludes my slides. We have the GitHub that includes all the documentation, tools, and examples, plus the Maxim integrated website with the part MAX78000 that has datasheet documentations, app note. And in the Hangout sessions, if you would like to join that, I'm going to show a number of video clips and demos, and Maxim technical team will be there. So feel free to join, and we're going to be available to answer any questions. Thank you very much for your time, and thanks for tinyML team for organizing this event.
Thanks, Afshin. That was great.
Again, just a quick shout out to our sponsors. Bear with me for 1 minute. We have different categories. We have executive sponsors. First one being ARM. Then we have Qualcomm. We have Samsung. Platinum sponsors. ADA Compute. Lattice Semiconductor. Gold sponsors. BrainChip. Babel Labs. DSP Group. Edge Impulse. EMSA. Gray Matter Labs. Greenwaves. HiMax. Imagimob. Latent AI. Maxim Integrated. Quixo. Reality AI. tinyML, Silicon Labs, Sentient, Google TensorFlow, XMOS, and lastly, silver sponsors, Edge Cortex, Hotchi, and Synsets.